I want to say this talk is actually dedicated to a great teacher of exception-safe coding. Many of you know that Yoda, in a galaxy far, far away, a long, long time ago, was teaching Jedi Knights how to use the Force. What many people don't realize is that Yoda is now teaching C++ programmers today to use the Force that comes from exception-safe coding. So let's talk about how we do that. I want to talk a little bit about the promise of exception-safe coding. And this is the bar that I expect you to hold me to. First of all, what I'm going to talk to you about is going to make your code easier to write. It's also going to make it easier to read. And by easier to read, I mean it's easier to understand and it's easier to maintain. It's also going to actually execute faster. That's not a big deal, but it will be a little bit faster. I'm sorry, I didn't mean that way. Being faster is a big deal. I'm not going to promise you a lot faster, only a little faster. But most importantly, your code will be 100% robust in the face of exception. Your code will be correct. It will be exception safe. So let's talk about this. The first thing I'm going to talk about is the problem. What is it that we're trying to solve? Why use exceptions at all? And then I'm going to talk about how people approach that problem without using exceptions. Exceptions are fairly new in the history of computing, and this problem that we're trying to solve is one that existed before. So there definitely are non-exception-based solutions. But then we're going to talk about the problems that we have trying to use exceptions. Exceptions are not trouble-free. And then I'm going to talk about how not to write exception-safe code. The blind alleys that people sometimes go on. And then I'm going to actually present to you the exception-safe coding guidelines. The guidelines that if you follow them will make your code easier to write, easier to read, faster, and 100% safe. And then I'm going to talk about some implementation techniques. And for those of you that are comfortable with exception-safe coding already, this may be the most valuable part of the talk. So I hope we get to it. So first question is, what is the problem? What is it that we're trying to solve? And in one line, it's the separation of error detection from error handling. So in any kind of code you're writing, whether it's a desktop GUI application, or whether it's an iPhone app, or whether it's a web service, or it's a driver, we have this common situation that we're faced with, which is that the code that understands the nature of what the application is, that's high-level code. This is the code that understands, how do I talk to the user? Do I put up dialogues? Do I send back HTTP codes? Do I log something to a file? Do I write to standard out? How do I talk to the user? That code's up here. But that code doesn't detect runtime errors. There's a C way up here. That code doesn't detect runtime errors. Where's the code that detects the runtime errors? That's at the bottom. That's down here where we're really doing the work, right? This is down here where we are trying to open files, and there is a chair way over here if you don't mind sitting from the side. The code at the bottom that actually detects the error is not the code that knows how to handle it. And the code at the top that does know how to talk to the user, knows how to tell the user, gosh, I can't do that because of this. It's not what detects the error. And so we have this separation, right? And this is actually good, because when we write libraries, we want the library to not have to worry about how I'm talking to the user way up at the top. The library is responsible for doing just what it wants to do. Are we trying to talk to a server? Are we trying to open a file? Whatever. And if you encounter an error there, somehow you just say, hey, I've got an error. And it's the code up at the top that has to say, oh, I need to tell the user there's an error. Right? And so that's what we're trying to do. That's the problem we're trying to solve. So let's talk about how we solve this before we used exceptions. And I shouldn't say before, because many people still use this approach. If you're writing C, you don't have exceptions, this is what you do. This isn't necessarily the only way to do it, but this is by far the prevalent way of doing it, right? So we are going to use return values for our error codes to express there's a problem. And so our functions will return this error value if there's a problem. Usually it's integral. Usually there's some well-defined set of what these error codes are. And the error codes are relayed up the call chain. Remember, the detection is way down here. What we're going to handle it is way up here. How do we get it up here? Well, every function has to return the error code. So what's the problems with that? Well, the first one is errors can be ignored. Okay? You call a function, you don't check the return value, or maybe you do assign it to something and you don't do anything with it. Right? So that's a big problem. In fact, errors are kind of ignored by default. If you just call a function, you don't do anything with the return value, you've ignored the error. The other thing is that it requires that everybody be on board with how we're handling this, right? If any function doesn't propagate the error up by its return value, then we've lost the error. The problems from the coder's point of view is this is very tedious to read and very tedious to write. It's not uncommon for code to have half of the lines of code are dealing with the errors, right? And that can obscure what you're trying to accomplish. We got a chair way up here. That can obscure what you're trying to accomplish. If we use exceptions, we address both of these very big issues. You cannot ignore exceptions. They just happen, right? And it turns out that it's much easier to write this code. The issue, though, is that exceptions have some. Oh, went too fast there. Exceptions have issues of their own. So let's talk about the dark side of exceptions. What's the problem with using exceptions? What's the scary thing?
It'll go up the chain and kill your program.
It'll go up the chain when you're not expecting it to go up the chain, right? I mean, on the one hand, that's the great thing. You can't ignore it. It's going to happen. On the other hand, that's the bad thing. It's going to happen, right? So what Yoda says is that exception unsafe code leads to bad states lead to bugs, and bugs lead to suffering, right? So we don't want exception unsafe code. This is what the issue is. It's code path disruption, right? The fact that we can't ignore the error code means that code can suddenly not be following the code path we expect, right? Almost every language works the same way. Line of code, line of code, line of code. Now, sometimes we have conditionals and we have some other things, some branching and things like that. But in general, I expect that after it does this line, it's going to do this line. And if it doesn't, because an exception comes whipping through, that's a little unsettling. That's what I call code path disruption. Right? And that's what we're learning, that's what we're going to deal with, the code path disruption. And in fact, I know this is a very long quote, but it's extremely target on. Jon Kalb wrote, counterintuitively, the hard part of coding exceptions is not the explicit throws and catches. The really hard part of using exceptions is to write all the intervening code in such a way that an arbitrary exception propagating from its throw site to its handler, arriving safely and without damaging other parts of the program along the way. That's the challenge. And when we don't get this right, that's exception unsafe code, and Yoda just said that leads to suffering, and we don't want that. So, just as an example, I want you to look at this code for just a little bit. This is actually a container, and it's a copy assignment, right? And what we're doing here is we're checking to see if what we're assigning from is us. What is that called? Self-assignment check, right? So we make sure that's not there. And then what do? Well, we destroy in place, and we fix this. There's a little bit of an attempt here to not reuse code, so we call the destructor when we destroy, and we call the constructor and do an in-place constructor. That's not used much now. This is kind of an old piece of code. The reason I wanted to point this out is that this isn't written by some idiot. This is written by one of my idols. Alexander Stepanov wrote this code. Who knows who Alexander Stepanov is? Who's ever heard of the STL? Who wrote the STL? Alexander Stepanov. Alexander Stepanov created the STL. This was his original implementation for it, and it was this way for 4 years. He was showing it to experts in C++ for 4 years before somebody said, you know, that's not exception safe. My point is, exception safety is not easy, but also, we've come a long way. Today, most of us can spot this immediately and say, wait a minute. What would happen if this new throws, if we're trying to create here, and this new were to throw, then we've left our object having been destroyed. And people recognize that now. People recognize that. As an industry, we've come a long way. We know how to, yes?
Can you define how you're using the word exception for this presentation? Because I'm hearing errors and exceptions. What I understand, like if you open a file and the operating system says that file doesn't exist, that's an exception, right?
Okay, when I say exception, I'm talking about a C++ exception. So that would be an exception if you have code that says throw something.
So I'm trying to translate this to many different languages. So in other languages, you don't have the exception structure that we have in C++. So in terms of what is an exception, you're dealing with error handling and anything that's outside of your purview, like for example the operating system that returns an unexpected state, like you open a socket and it's not available or something.
Okay, so you touched on several issues. The one thing is, I'm not certain how well what I'm going to say does translate. This is really, really concentrated on how C++ semantics work. And so, in a general level, these ideas all translate.
Yeah.
The other thing is that exceptions and errors are not exactly the same thing, but they're very, we use exceptions to handle errors, which as I just said, that's the problem we're trying to solve, is that error problem. In theory, you could use the exception mechanism as a control flow mechanism, right? You could say, in fact, I had a professor once who pointed out, he said, you know, we declare a function, we say it returns an int, but you can actually have a function return anything you want. You just throw whatever it is. That's a really, really bad design. Don't do that. Please don't do that. Anyway, so, yeah, I'm going to have to make the distinction that when I say exceptions, I mean throw exceptions. And this may not translate into generic sense. And I'm sorry about that. Anyway, the other thing, and the reason I brought up that slide was, again, not because I'm trying to say, oh, what a bad programmer he is. He's my idol. He works in A9, by the way. You can come and join us. Send me a resume. So, how many of you have heard of Joel on Software? Great. You guys are well read. Okay, so Joel on Software is a blog. He's talking about quality software. I once went to a Joel on Software, a particular blog, and I saw this and immediately stood out because this was the code. You know when you look at a page, what do you look at first? You look at the picture, you look at the headline, you look at the code. This was the code. I looked at that and I immediately said, oh, that's wrong. And what was funny about that is, that was the point of his talk. That was the point of his blog. He was saying how to make wrong code look wrong. And I said, well, mission accomplished, that looks wrong to me. But that's not the point Joel was making. Joel was saying, look, this doesn't look wrong. It did to me. But he said, it doesn't look wrong. This is, remember we said code path disruption. This is going to happen, and this is going to happen. This is what programmers expect. It looks safe, it looks good. But Joel's saying, wait a minute. What if do something throws? Your cleanup's never going to happen. So what was his conclusion? Exceptions are extremely dangerous. I'll get back to Joel. First I want to talk about the wrong way. These are things that if you had asked me maybe 10, 15 years ago, how would you write exception-safe code? I said, well, I don't really know if I have it completely figured out, but I know the first steps, and these are them. And this is what I would have told you. I would have said, we're going to check all the return values in error codes, and we're going to detect exactly what's gone wrong with the program at every step. I would have said, you're going to have to identify every function that might throw. You're going to think about what happens if this throws. I would have said, use exception specifications, because that way the compiler is helping you do your job. I would have said, use these catch-try blocks to control your code flow, right? Yoda says you must unlearn what you've learned. This is not the right way. This is not the right way. Let's talk about the right way. Let's talk about exception-safe stuff. How to write exception-safe code. Before we do that, we're going to talk about the exception safety guarantees. This is attributed to Dave Abrams. He's one of the big movers and shakers at Boost. And so he has identified 3 safety that every function has to fall under if you're going to have exception-safe code. The basic one says the invariants of the component are preserved and no resources are leaked. So if I call a function and that function throws, is there any guarantee about the state that the object's in? No. It may have gotten halfway through whatever I told it to do and then it throws, right? But can I destroy the object? The invariants are preserved. That means I can still use the object. I don't know what state exactly it's in, but I can still use it. I can destroy it. And also, no loops. All right, the next guarantee is the strong guarantee. Here he says the operation has either completed successfully or thrown an exception, leaving the program state exactly as it was before the operation. How many people have done some database programming?
Yeah.
This is a transaction, right? It either did or it didn't. Okay? And then the last one is no throw. The operation will not emit an exception. The emit is key there, but we'll talk about that in a second. Yoda has this to say about the strong guarantee. This is what Yoda says. Do or do not. Right? Okay, so let's talk about this from the implementer's point of view. We always want to strive for the strong or no throw guarantee. Now, the strong guarantee is saying what? The strong guarantee is saying if you can't do what you're supposed to do, leave everything exactly as it was. It turns out that that's actually pretty easy to do most of the time. We certainly don't want to do it all the time. Imagine I have a container. Think about a vector. And I'm saying I want to insert. Well, what happens when I insert? Well, what I'm going to do is I'm going to move everything down, and I'm going to insert, right? I'm going to copy it in. And the moving, any of those moves could throw, right? So is it possible to make an exception, a strong guarantee of an insert in a vector?
You back it up first.
That's right. You could make an entire copy and then do whatever you want to do, and if you fail, say, ooh, throw your exception, restore your copy, and throw your exception. But who wants to use that kind of code? How expensive would it be? Every time I make I try to do this, right? But it turns out there will be times in your programming when you need to do that. So you'll have to do that. You'll have to do that outside. But that's okay. The point is, in many, many cases, strong comes, we say, free. If you've done basic, you get strong. In some cases, you can give and get no. So let's talk from the caller's point of view. The caller is going to assume basic. In your role as a caller, remember I said before, we try to identify all the functions it can throw and figure out, no, assume they throw. Assume everything throws. Now we're going to make some exceptions. We're going to have some that don't throw, but most of the code that we deal with, we just assume from the beginning that it throws. The strong or no throw are only needed sometimes. In order to write exception-safe code, some things must be no throw, and we'll identify what those are. First thing we're going to do is we're going to talk a little bit about the mechanics. For those of you who are experienced with C++, this is all review. We're not going to spend much time. First, let's talk about the throw part. This is where we have error detection. We say throw an object. This is almost never how we do it. What we usually do is we create the object when we throw. Say throw, here's the type, here's the constructor parameters, that's what we throw. Right? That's typical. One other thing we can do is we can say throw with nothing. How can we say throw with nothing?
It throws whatever.
If we're in a catch, whatever has been caught can be rethrown. So this is usually read as rethrow. Even though it says throw, the re is silent. Or it's invisible. It's not silent, we read it. Okay. Anyway, so that's all we want to talk about there. Let's go back and let's talk about the other side. Catching. Alright, so we have a try block, code that can throw, and then we have some number of catches. Cannot be 0, can be 1, can be number greater than that. The last, if a ... is there, it has to be last. That catches everything. It's usually called catch-all. And each one of these guys is in its turn going to try to match what it catches with what the actual exception is. If there's a match, we do that block of code. We do not check further. We never execute any other block. At most, we'll execute one block. If there is no catch handler, it's possible nothing will catch, in which case none of these blocks are executed, and we continue outside up the stream looking for catch. I hope that was a review for everybody. I know I went really fast. All right. So if we were to say throw A here, what could we catch it with?
Let's see, string.
We can catch it with A.
Yeah.
Turns out there's a lot of things we can catch it with. We can catch it with A, we can catch it with reference A, const ref, volatile, const volatile ref. We can catch it with B if B is a public base class of A. We can catch it with a ref B, const ref, volatile, const ref. If A is a pointer, could be a type def, we don't know what A is, could be a type def to a pointer. Then we can catch it with void pointer, void star, excuse me. And of course we can always catch it with catch. Right? So what happens if we catch A like this. What's going on?
Go copy it.
It's going to do a copy. What happens if we catch A with B?
We'll lose whatever.
It's going to slice it.
Yeah.
It's going to slice it. We don't want that doing, right? So here's our guideline. We throw by value. We catch by reference. Okay? Throw by value, catch by reference. What is throw by value? Well, first of all, it's syntactically not legal to throw a reference. But you could throw a pointer. You say, oh, I've got this object, I want to throw it, I'll throw a pointer. Turns out that's usually not a good idea. If you have a pointer to something that's on the stack, that can be cleaned up. In general, don't do that. Throw by value, catch by reference. You see this here? There's a few places where I have an asterisk saying, this may be a little different in C++ 11. In C++ 11, there's lots of cool stuff having to do with exceptions. You can actually arbitrarily create an exception in an exception pointer, hand that exception pointer off to another thread and tell that thread to throw at some other point in time. Just all sorts of really stuff. And I'm not going to pretend to be an expert in that stuff. I can talk about it, but I'm not going to. Instead, I just tell you, this may be a little bit different for C++ 11. So let's talk about the cost of a try-catch. It turns out that if you don't throw, there's no cost. Anybody believe that? It's really hard to believe, but the truth is, with modern compiler technology, there is no time cost. It turns out that in order to make this happen, compilers create a whole bunch of tables to figure out what the code's going to do. So your code can be bigger. Most of us don't care, right? I mean, when you sit down and write the code, you say, oh, I got to write this code as tight as possible because I don't mean, no, we've got these multi-gigabyte machines, stuff like that. If you're in a really, really memory-constrained environment, this might be an issue. But for the vast majority of us, code size is not an issue. So for our point of view, we'll say that if you don't throw, there's no cost. Ah, but what if you do throw? What if you throw? Then what? Yeah?
I just wanted to make a small comment. If you compile this debugging information now, GCC shares this table with the debugger, so even your code will not become larger.
Oh, interesting. Oh, that's interesting. Thank you, Ronnie.
Yeah.
Ronnie's giving a talk at 5, by the way. She knows a little bit about debugging. Go and talk to her. Where is it? What's the name of it?
It's debugging of concurrent programs on Linux.
Okay. All right. So, in the throw case, what does it cost? I don't know and I don't care. The idea is that if we've hit an exception, this isn't a normal path. I'm no longer worried about performance. I'm worried about correctness, right? If you have a program where in your inner loop you expect lots of exceptions to be thrown, you have a problem with your program, right? That's a bad design. So, in the case where we don't throw, performance is really critical, and we get the tries free. But when we do throw, yeah, performance is out the window, but we're not caring about performance in that case. We care about getting it right in that case. Don't crash. So I'm going to talk a little bit about some of the standard handlers that we have to deal with. The first one is called the terminate handler. This is a standard handler. It's called when we rethrow and there is no exception. Remember I told you about rethrow earlier? I said if we're in a catch block, right? What if you just out of the blue say, oh, throw. I'm not in a catch block, but throw. I'm going to call terminate. It's also called when throwing when there's already an exception being thrown. Right? And that calls standard abort. Now it turns out, you probably don't want to just abort our program. So we can write our own terminate handler and we can install it. Unfortunately, there are a lot of legal restrictions on what you can do in your terminate handler. So it turns out that although we can write our own, it's too late. You could log, you could do whatever you want, but you're probably going to end up calling abort or something like that. Right? The game's over. The key is don't call terminate. All right. So how do we not terminate? Well, let's go back. How do we terminate? Well, if we call rethrow and there is no exception, right? Or if we throw when there's already an exception. We got to avoid those two situations. Well, don't rethrow outside of a catch block. Well, that's pretty easy. That's not an issue. We just have to know we're not in the catch block. We're going to do a rethrow. But what about the other one? Don't throw when an exception is being thrown. Well, wait a minute. Okay, so we hit throw. We throw. We catch. Well, there's no code in there. We don't have to worry about that, right? is no code that gets executed from the time we hit throw to the time we handle it, right?
Structures.
The destructors.
I have a question.
Yeah.
There's a cost in throwing, right? Is that a runtime cost or more like a space cost? You know.
Is there a time? I'm sorry, I missed it.
You mentioned there's a cost when we throw, right?
Yes.
Is that a runtime cost or is this more of a compile time? I mean.
No, there's a runtime cost. Yeah, absolutely.
Even if you're not hitting it,
If you throw, there's time involved in figuring out what you're doing. Yeah. I don't even know what it is. I don't care. Well, I kind of care, but not too much. But yeah, there's a runtime cost. If you're throwing, you've hit your performance. All right. So what we're talking about is exceptions being thrown after exceptions are thrown. Doesn't make any sense, but it turns out yes, destructors.
Never.
Because what's happening is any object that's on the stack, whether it's in the function I'm throwing in or any function that's inside that function, that's going to get cleaned up. That's unwinding the stack. So when we call throw, the compiler, the runtime, I should say the compiler, the runtime is responsible for seeing to it that every object on the stack gets its destructor call, and it unwinds the stack back up to the catch. Right? And so what does that mean? That means there is code that's executed. All right, so that leads us to our next guideline. Destructors must not throw. They must deliver the no-throw guarantee. Cleanup must always be safe. Okay? Now, you might have a situation say, well, I got to know if I try to close a file and it doesn't close, that's really important. Yes, it is. Yes, it is. We may need to log it, we need to do whatever, but if it's really important, you need to make certain that you close it before you unwind that stack, or whatever, because you cannot throw from a destructor. Now, notice, remember before I said the no-throw meant we don't emit exceptions? Turns out it's actually legal for you to call logging or some other code that might throw, as long as you catch it. If you catch it in the destructor, that's okay. It's okay for you to throw in a destructor. It's not okay for you to throw out of a destructor. You need to catch it and prevent it from rethrowing. Okay, how are we doing on that? So here's another standard handler. There's only two, so it doesn't take too long. The unexpected handler. This is called when you throw outside of exception specifications. We mentioned those briefly earlier. But let's talk about this. Unexpected, when you throw outside an exception specification, and that calls terminate. And what does terminate do? That terminates our program. So we don't really want to do this, right? Again, you can write your own, so you don't call terminate, but it turns out that if you follow all the rules in the language, you can't just, oh, I'm going to ignore this problem and move on. No, you're over. It's done. So let's talk about what exception specifications are. This function has no exception specification. It means it can throw anything. Now, in practice, it may not. It could be C function, right? But it could throw anything. We're not specifying that it doesn't. This can throw A or B. We've said throw A, B. It means it can throw A or B. Or things derived from A and B. This, because it's empty, may not throw anything. So those are exception specifications, right? So, what exactly does that mean? Well, the interesting thing about that is that exception specifications are not checked at compile time. This is not Java, this is C++, right? And so, if you're calling a function and the compiler says, oh, I noticed that function throws an exception, but you didn't say you threw that exception, and you're not handling it, oh, I'm going to assume that the way you're calling it is such a way that it could never throw that exception. You're an adult. You're a C++ programmer, and if you say your exception, then that's what it is. It doesn't check the compile time. But what it does do is, it's enforced at runtime. How is it enforced? Well, that's what we're talking about, is that standard handler. If you say, I only throw A or B, and then you throw C, which let's say it's not derived for A or B, you throw C, what happens? At runtime, it checks and says, okay, let's see what kind of exception this is. Oh, this is abort your program. This is almost certainly not the behavior you want at compile time or at runtime. So, that leads us to our next guideline. Don't use exception specification. In C++ 11, there's a new thing that's actually called no except. And you can decorate your functions with no except. I'm not going to say any more about that. Come back next year, we'll talk about C++. Let's talk about safe objects. Exception safe code is built on safe objects. The first thing we need to talk about is object lifetime. So let's say I've created a class. I want to talk about the order of construction. Right? What is a class? It has subcomponents, it has base classes, it has members, it has stuff, right? If I have a class and I'm calling its constructor, what gets constructed first? What's the order of construction? What's constructed first? The base class? Okay. Suppose I have multiple inheritance. Which base class?
The first one listed.
What's that?
The one that's listed first.
Right. As listed in the definition left to right. Right? Okay, what's constructed next?
The member variable.
Data members. In what order?
Where they're declared.
The initializer list of the constructor.
No.
No. No. It's as listed in the type definition top to bottom. Not as listed in the constructor's initializer list. Why not?
It will yell at you if you do it out of order in the initial. Because you can have stuff that's not in the initializer list.
Well, you can put the initializer list in whatever order you want. You may have a warning.
Yeah.
That's not a compiler. The reason it's not in the initializer list is because you can have multiple constructors, which means you could have multiple initializer lists, which means you could initialize things in different orders. Well, one of the important things about C++ is the promise is that destruction is always the reverse order of construction. So if you constructed things in different orders, the object would have to know, oh, I got constructed by this constructor, so when I destroy, no, we don't go down there. So it's as listed in the definition, not in the initializer list. Don't let that, sometimes we have data members that have to be created in a certain order. Make sure you get that right here. This doesn't help to get it right there. Okay. Oops. Well, and then what happens? What's initialized next? The body of the constructor is called, right? So, base classes, data members, and then the body. Okay, what's the order of destruction?
Backwards.
It's the exact reverse order. So we're going to call our destructor body, then we're going to destroy our data members in reverse order of the definition, and then we're going to destroy the base classes right to left. Right? Okay. Now, here's a question, and let's not get too philosophical here, but when does an object's lifetime begin?
What object?
After initializer list is,
After the initializer list?
After the constructor is run.
Okay, we have a difference here. You're saying the initializer list, he's saying at the end of the constructor body. That's what you mean.
You can't destruct it after, before, like, you won't return the object until the constructor is finished. But
Okay.
it will. But if something error occurs during the construction, any members will be destroyed.
Okay. All right. All right. We're getting there. The answer I'm looking for is at the end of construction, when the object is completely constructed. Okay? And the reason I'm looking for that answer is not just to be weird, because I want to talk about aborted construction. And how can we abort construction? You could throw from the constructor of the base class, constructor of any of the data members, or constructor body. That's how we would abort construction. Right? So let's think for a minute about what we need to clean up. So I'm writing a class, and I know that my base classes may throw, my data members may throw, and my constructor may throw. What do I need to worry about cleaning up? Do I need to worry about the base class object? No, because if that's written properly, it will clean itself up. Do I need to worry about data members? No, because if they're written properly, they'll clean themselves up. What about the constructor body?
Yes.
Yes.
If
Oh.
within the constructor body.
But I have a destructor. Can't I clean it up in the destructor?
Destructor
No,
is not
not
called
built
a
in.
destructor.
Exactly right. Exactly right. So that's why I was saying, when does the lifetime of the object begin? The reason that's important is because the destructor will not be called unless your lifetime has begun. So if you throw an exception out of the constructor body, your object has not begun to live yet. And so the destructor will not call. So if you do anything that needs to be cleaned up in a constructor, you need to make sure it gets cleaned up. Because the destructor will not be called. Okay? What about new array? What if somebody makes a whole bunch of me in an array? It turns out that the runtime handles that. As long as I clean up the constructor body, the runtime will make sure everything's handled properly. What about the object of the member itself? Not what you're calling new, but the object itself. Will that leak if I throw an exception?
What do you mean?
So if I say new something, and in the constructor I throw, will I leak that the object's memory? No. For the exact same reason as the new array. The runtime is responsible for that. Okay. All right. So now I want to talk about RAII. Who can tell me what that stands for? If you can't read, you're pretty bad. Okay. So let's talk about well, I should talk about what this means. Resource acquisition is initialization. This is Bjarne Stroustrup's phrase. I think it's awful for two reasons. I'll talk about one now and one later. The reason I think it's awful, first reason is it's just a mouthful and nobody really knows what it means. But actually it's very, very interesting because it can be read two ways. So the two ways to read it are, one is you can say, I'm writing a program, I need a resource. I need a network socket. How do I get a network socket? Well, according to Bjarne, you initialize something. There's an object, and when you construct that object, you get the network socket. In other words, it's going to get the network socket in its constructor. The other way of looking at that is, I've got some object I need, and I'm going to create the object, and by the way, it needs a network socket. Where is it going to put the network socket acquisition? In the initializer. So you can look at it either way, but what he's saying is that resources are acquired in a constructor. Okay, so let's talk about some examples, because you probably use this without even thinking about the fact that they work. Most smart pointers work that way. Wrappers for memory, files, mutexes, network sockets, almost anything. If you're in a C++ framework, you almost certainly have a wrapper for these kinds of objects. Right? So what happens to the object if acquisition fails? Nothing happened. Well, why does nothing happen? Because the object never exists. Why does the object never exist? Because if you throw an exception from the constructor, the object never exists. So what we have is, if you have the object, it means you've got the resource. What we've done is, we have converted the failure to acquire a resource into an exception. Very powerful concept. Anytime in our system where we can't get a resource, it means an exception's been converted. And we don't have to worry about zombie objects. A zombie object is where, oh, it's supposed to be a network socket object, but there's not really a network socket there. You have to call it first and say, do you actually have a network socket? No. It's a network socket object. It has a network socket. Okay, so the cleanup responsibilities for this object, the destructor has to release any resources. Some objects may have a release member that lets you release it early. That's not that important, but it's a footnote there. But the important thing is, cleanup cannot throw. Why? Because destructors cannot throw. If you're going to write exception-safe code, you have to live with it. All right. So, I want to talk about a design guideline. This is much bigger than this talk, but the design guideline is each item, whatever it is, function, type, anything we're writing, has one thing to do. One thing to do. This is one of my biggest problems because I always start out and here's this function, it does this thing, and later, oh, I want to add this little thing, and pretty soon it's really complicated and it's a mess. Right? This is good design. One thing does one thing. So from this we get no object should manage more than one resource. Now, I will point out, if you have a vector, well, what is a vector? It's got a bunch of things in it. Okay, I don't want to go there. What I'm talking about is, let's say I've got some object, and I'm going to read from a socket, I'm going to write to a buffer, and so the object is managing both the socket and the buffer. Don't go there. If you have an object that needs to do that, make a small object that's a data member that handles the network socket, and another small object that's the buffer handler. And don't handle two resources. Delegate those. Each object, right? Every constructor, every resource is an object. Okay? If it isn't an object, it isn't going to be cleaned up in a destructor. Good luck. Smart pointer to your friend. Shared pointer, now part of the standard. If you don't know that shared pointer, you should learn about it. Now, let's talk about state. So what is state? So let's suppose I'm writing a graphic application, some kind of GUI, and the user, somebody's calling me to write, excuse me, I'm going to write something to the screen, but in order, what I'm writing is really important and it has to be seen, so I change the foreground color to red. Right? I need to restore that, right? That's a state that I'm setting. If I just restore the foreground color to red, write whatever I'm going to write, and then return, my caller is not going to be happy. Right? Because I need to, if I'm changing the state, I need to restore the state. So, I'm going to treat that state as if it's a resource. Right? So I'm going to have an object that handles that state. Remember when we talked about resource acquisition as initialization, I said two reasons I don't like it. One is it doesn't really roll off the tongue. But the other is I don't like the word resource. Why? Well, one reason is because resource includes too much. So, let me say what I think is a really cool resource. Every modern OS has this. You can call some function in the OS and you can get the current time. Think about that. There's certain kinds of classes of applications we couldn't write if we couldn't find out what time it is. That's a really valuable resource. But do you have to manage that? You have to say, oh, I called time, I better call untime. I better release the time. Right? No, you don't do that. It's a resource, but it's not what we're talking about. The other reason I don't like it is it includes too little. Is changing the color of the foreground, is that a resource? No, it's a state. It's not a resource. So, here's what I like. Responsibility. Because that's what we're really talking about, right? If you're doing something that you have to undo, you've acquired a responsibility. And so I prefer responsibility acquisition as initialization. I like to talk about responsibility leaks or responsibility management. Because I think it's a more accurate descriptor of what we're really trying to say. If you allocate a buffer, you're responsible for that. If you change the foreground color, you're responsible for that. So you've acquired a responsibility, and if you're writing exception-safe code, you have an object on the stack that captures that responsibility and discharges the responsibility when it goes out of scope. And so it can go out of scope whether you simply return from the function normally or whether you throw an exception. So here's our guideline. Use RAII. Responsibility acquisition is an initialization. Every responsibility is an object, one responsibility is an object. Cleanup code. Don't write cleanup code if it's not being called by a destructor. The destructor is responsible for cleaning up all the outstanding responsibilities. Be suspicious of cleanup code not called by a destructor. Remember Joel? You see now why I looked at that and I immediately said, that's wrong. Right? This is a textbook example of what I think you should never do. You don't just call cleanup code. It should be in a destructor, right? This is how I think it should look. Right? We have some cleanup object. In its destructor, it's going to call cleanup. Then we can call do something. If do something doesn't throw, we clean up. If do something does throw, we clean up. Exception safe is exceptionally safe. Right? It's not dangerous at all. It's not dangerous. So here's our guideline. All cleanup code is called from a destructor. An object with such a destructor must be put on the stack as soon as calling the cleanup code becomes a responsibility. As soon as you acquire the responsibility, you make an object that will discharge that responsibility in its destructor, and you put that object on the stack. Yes?
So, to make it simple, do you just like bind a function to a destructor via a boost or something to make the...
You could, but if you were going to do that, you put that in the implementation section at the end of the talk. Okay? Yeah, exactly right. Okay, I want to talk about the Cargill widget example. So, Jon Kalb, another one of my idols, remember I quoted him in that really long slide earlier. He wrote the best technical article I have ever seen. That's where the quote came from. It's in the bibliography. So go to the session, first do the feedback on the feedback, then go to the session wiki, and then get the bibliography, and then look up Tom, which by the way is online, you can get it free. But anyway, so what he said is, imagine we have some widget. And imagine that widget has a couple of members that could be anything. And imagine that we wanted to write the copy assignment. So this is a value class. So we're writing a copy assignment operator. We want this to be the strong guarantee. Here's a review. What's the strong guarantee? It's the transactional one, right? If we throw, nothing's touched, right? So he says, can we write the strong guarantee in this case? Well, what's the challenge? Well, the challenge, of course, is that if you update this, and that's okay, then you have a problem doing this and you throw, then this has already been updated. That's the problem. So the easy way is, well, update this one first, and then... Well, here's a way we can do it. So let's capture the value of the original, then update the original. Then if you update the second one, and that throws, then you can restore the original. Problem solved, right?
If they're big, that's horrible.
What?
If they're big, that's horrible.
If they're big, this could be expensive. Right? But that's not the real problem. The real problem is what? This could throw. We haven't really solved the problem at all, right? Well, okay, we could capture this value and then we could... Okay, so what was his point? His point was that exception safety is harder than it looks. Anybody disagree with that? All right, you either don't have a hand or you agree. It can't be bolted on after the fact. What he's saying is you have to design with exception safety in mind. And it needs to be designed in from the beginning, right? And so what was his answer? His answer is no, you can't do that. Just to be difficult, I say yeah, you can. And I'm going to show you how it will work. Some of you may think that I'm taking you on a road, a little voyage on the Kobayashi Maru, but that's the wrong universe. We're in a different universe, so we won't talk about that. All right, so let's talk about fundamental object functions. The constructor, the default or copy, destruction, and copy assignment operator. This is for value classes. So I'm basically talking about value classes. This is true for anything. This is true for value classes. How many of you heard the rule of three? Okay, you guys need to read more Scott Myers. It's on the bibliography. Read more Scott Myers. So the rule of three is saying, if you write a copy constructor, a destructor, or the copy assignment operator, you probably need to write all three. Now, why is he saying? Well, what he's really saying is, if you're writing any of those, that's a symptom that you have some responsibility or some resource you're managing. And if you need to manage that when you copy it or create it, then you probably need to discharge it in the destructor. And if you're discharging it in the destructor, you probably need to think about what you're doing with assignment, right? Sorry, my voice is starting to go, I think. I think Scott Myers is brilliant, another one of my idols. But I don't think he went far enough. I think we need the rule of four. There's one more fundamental operator that he hasn't talked about. It's called the swap operator. And it looks like this. Swap is defined in the standard library. It's an STD, right? But the thing is, the standard swap is not no-throw. Remember I said there are certain functions we have to have that are no-throw. Not many. Most of them, basic guarantee is fine, they can throw. But certain functions have to be no-throw. This is one. Swap has to be no-throw. So it turns out that although the standard swap is no-throw, when we create our own types, almost always we can make sure they're no-throw for our types. All right, so let's talk a little bit more about this. The swap operator, you want to always spell it swap, lowercase, even if your coding convention says function names. No, this function has to be this way. It's too bad there isn't some cute little, top of the keyboard squiggly little symbol for it, but there isn't. You have to actually spell it out. When we write our class, remember I'm talking value classes. So when we write our class, we want to write a 1-parameter member function and a 2-parameter free function in the standard namespace. If your type is a template, don't put it in the standard namespace. We'll talk more about that. Both parameters take by non-const reference. Now that has to, right? Yeah. If you did it by copy, you can't swap. And if you did it by const ref, you can't swap. So it has to be non-const ref. Right? Does not throw. It is not written like this, even though it doesn't throw. Why not? Why don't we write it this way, even though it doesn't throw? Because we don't use exception specifications. That's the guideline, right? We don't use exception specifications. Okay, so here's our example. Big int. Big int is just it's a class I'm writing where it can't overflow. If I need overflow, I allocate more space to hold the number of bits that I need, right? So that's what a big int is. And what I do is I create a swap, returns void. It's a one parameter because it's a member, and it takes it by reference, not const, non-const reference, right? And I have a comment, not an exception specification, saying that doesn't work. Now let's think for just a second. Is that going to be hard to implement? Well, it turns out, if you think about it, any class we make, it's made up of what? It's made up of either fundamental things like ints and floats and pointers, or it's made up of some class that we've defined. That's the only thing it can be. And what is a class? Well, a class is made up of, if you keep drilling down, everything has got to be either a vector, either an int, or a float, or a double, or a pointer to one, or something like that, right? And all of those can be swapped without throwing, right? So if I'm writing my own class, I should be able to write it no throw. All right, so let's talk about what I said before. In the standard namespace, we want to create a swap with two parameters, right? And it turns out the implementation that's very simple. We just call the member swap of one of them, swap the other. Remember, if you're swapping, they better be the same type, so it doesn't matter which one you call them. Okay, now here's the deal. The standard has a definition for swap. So the first question is, are we allowed to add things to the standard namespace? Is that legal for us to add to the standard namespace? No. Well, the answer is yes and no. The answer is no, you can't add anything. If it's not there, you can't add anything to it. But the answer is yes. You can specialize something that's already there. So technically, we're not adding anything new, because swap's already there. We're not adding swap, we're specializing swap. It's legal to specialize something in the standard namespace if we're specializing it on one of our types. You couldn't specialize it for int, because that would sabotage other people who would try to swap ints. But for our type, we can specialize. You can't do it for standard library types like vector, but you can do it for our type. So this is a specialization. So we say template, empty brackets saying I'm specializing an existing template called swap. I'm specializing it for the type where the type is big int, and I have these two parameters, and I just call this. Okay? Everybody understand that? All right. Let's do another example. This example is a template. It's a container of some sort. It's a circular buffer of some type T, and just before, swap, circular buffer of T by ref, non-const ref, documented no throw, and what we do is we swap all the bases and all the members. Okay? Not in the standard namespace, we have a template T, and we define swap with two parameters, and we call the one parameter member. Why is this not in the standard namespace when the other one was?
A template.
It's a template. Well, why does that make a difference?
I don't know, you want to tell me?
I am about to tell you. Remember I said we could specialize things, right? A specialization is when we say, these are the types that this template uses. But we can't specialize this because we don't know what type this is, right? So what do? We would use a partial specialization. You know what a partial specialization is? That's where you're saying I'm specializing some of my template types but not others. And you can do that for a class. But in C++, you can't do that for a function. Instead, we overload. And the syntax looks exactly the same, right? But it turns out that an overload you can't put in the standard namespace. So we do it in our local, just to be legal. Okay, so why no throw? Well, it turns out that is the whole point. That's what we're trying to do. Standard swap is always an option. We could save all this trouble if we didn't want it to be no throw by just using the standard swap. What does it do? It does 3 copies, right? Okay, how would you implement swap, right? You copy this to a temporary, you move this over here, you move this down. That's it. But the problem is, those could throw. So that's why we have to do our no throw. Excuse me. So by custom swaps, we can make no throw. Don't use non-swapping base classes. Don't use const or reference data members. Those are not swappable. So this is, by the way, this is for, remember, value classes. Sometimes it makes sense to use these sorts of things in reference classes, but for value classes, no. This is how, if we're in a template. The problem is, how do we call it? Because if we said std swap, we're in a template, we don't know what this type is, right? And so if we call std swap, we would insist that we look in the standard namespace for the swap. But we just got through saying that it's possible that we'll define a, way back. We might define this not in the standard namespace. So we don't want to say standard swap when we call swap, right? So instead, we say using standard swap to pull it into the current namespace, and then we just call swap, and the compiler will find the right swap. If that's confusing, there's an alternative. You can just do this. Include boost swap and call boost swap. That does the right thing. Yoda says the force is strong with this. So our guideline is create swap operator for value classes. Must deliver the no throw guarantee. Now I'm going to talk about how to implement the strong guarantee. Remember I said strong guarantee is often free. Just implementing the basic safety, you get it. And the way we're going to do it is we're going to say, we're going to defer the commit until success is guaranteed. So what does that actually mean? As Yoda would say, do or do not, there is no trouble. Here is a resource owning object. It owns this M resource, whatever this is. It's a type resource, pointed to that. And we want to make a copy assignment for this. So what do? We delete the one we have now. In order to make room, we call new, we call it copy new, and we do this, right? What's the problem?
You can throw in new.
What?
You can throw in new.
Okay, that's true, but I don't want to hear that answer. What answer do I want to hear? What answer do I want to hear? We didn't check for self-assignment. First thing we do is we delete this. Well, what if we were copying from ourselves? What if RHS is this? Right? We just deleted this, and then what? We said new, one of these. Whoa! We got a problem, huh? Right? Yeah. I think I need a. I think I need a splat there. Everybody's ever pointed that. Okay, so let's fix that. I'm going to check for self-assignment here. Now, what's wrong with it?
Now you can throw.
Now it throws. Okay, so what happens? This new could throw, right? And if new throws, what happens? Well, this object is going to exist, but we've deleted M resource. No, we didn't zero out M resource. So it's pointing to an object that doesn't exist. Very unsafe. Now, of course, we could, after we delete, we could assign it to 0. That's not the point. The point is not just that it's pointing the wrong thing. It's that we have an object that we've left in a bad state. So let's see if we can address this. One thing we can do is we can make a temporary, right? Create a temporary, and then we use swap. Is swap there? Yes, because we're following the exception safety guidelines, which says yes, we make swaps, right? So then we swap this, right? Is this exception safe? Well, let's think about it. Could this throw? Could that throw? We're creating an object. We don't know. It may have a buffer. I don't know. There's all sorts of reasons. Yeah, I could throw. If it does, is our object modified? No. Strong guarantee holds. Okay. What about this one? Can this throw? No. You better say no to that. This can't throw. This can't throw. We're gold. Right? We either fail or we succeed.
At the cost of copying the whole thing.
At the cost of creating a copy resource. That is correct. That is absolutely correct.
But you do that on a large data structure. I mean, you just basically halve the speed of your application all the way through. I mean, yes, it's exception safe, but the penalty's huge.
We will get better. What you say is actually true. If we couldn't get better, I would still respond and I would say, look, we are doing something that's guaranteed to be robust and handle the problems. I almost can guarantee you that if you try to do some other approach and you're also robust, that's also going to slow you down. But it turns out that we can have our cake and eat part of it anyway, too. Yeah.
Is the swap function copying, or is it moving around pointers?
You implemented swap. What did you do? If you implemented a no-throw swap, then you probably didn't do any copying, right? Except you copy pointers. You copy all your pointers to a temporary and, right?
So, I mean, there shouldn't be any copy.
It should not be expensive. That's right.
Because
That's right.
you were going to copy anyways.
So what he was talking about was a very large object. Okay, so if the reason your object's large is because, let's say, it's a bitmap.
Well, lots of smaller objects and a throughput of a string or something.
Yes, if it's lots of ints, let's say you have an object and it's got 1,000 ints, then it's going to cost you 1,000 int copies to do that swap.
Any database interactions is heavy in binary data. That's going to kill it.
But you're using a. Are you assigning it the objects, or are you doing like that?
Okay, so the model is that anything that's really expensive to swap, you're going to want to have a pointer to it. So it makes it cheap. Swap should be cheap. It's not guaranteed to be cheap because you could have an object with 1,000 ints, and if you didn't put those off in some object that you got a pointer to, it's going to be expensive to swap. There's no way around it. In general, this turns out to work. We'll get it faster. We'll get it faster, I promise. The first thing I want to talk about, though, is the critical line. So the critical line says that objects that need to be modified, we make copies of them, then we modify them, then we do whatever the commit needs to be done. We do the swap, right? So whatever we're going to modify, we make a copy of it, we do the modification, and then we swap it. Do you understand why? The reason is this has not modified but can fail. This cannot fail, but we'll do the commit. So let's apply that back. Let's put, this is the code we had just a minute ago, and I've added the critical line. This is what could fail and hasn't modified our object at all. And then once we know that we're down to here, if we haven't thrown yet, we will not throw. So it's safe. So this is actually the way a lot of people will write this. And it turns out it's hard to write the critical line because the critical line is, right about here. But it's implied there because in C++, this will be executed before this. So what can fail is executed before the swap, which is what commits are. But this is how I want you to write it. Not this way, even though this is clever. This is how I want you to write it. So first of all, we've got our object swap. We're not swapping resource this time. We're going to swap the entire object. So we've got a no-throw object swapper, right? And notice that we take the object by copy. This violates the training of C++ programmers, right? How do we take objects? If we're going to modify them, we take them by ref. If we're not going to modify them, we take them by const ref. If you're going to copy an object, let the compiler copy it for you. That's what's happening here, right? And we already said you have to make a copy. We said that, right? In our body, we had to make a copy. I'm letting the compiler copy this for me. Why am I doing that? It turns out there's a very, very interesting optimization that happens in compilers. The compiler can very often determine when you are passing something in by value. In theory, the compiler always needs to copy it so that you have your own copy. But in practice, very often, this is an implementation, and this is an optimization in all the compilers that are out there. The compiler will recognize, wait a minute, what I'm giving you is something that is going to go away. I'll just let you have this. I'm not going to have to make the copy. The copy can be elided. So, for example, suppose that this assignment operator is using the return value of a function. The return value of a function is about to go away. So the compiler will recognize, I don't need to make this copy. There's no way in your code you can know that. Not in C++, the old standard. New standard you can. That's what move semantics is all about. But this is exploiting move semantics in classic C++.
Could you explain that? Could you explain that some more? You're saying that the resource is coming in by copy,
No, a value, not necessarily copy. That's the key.
But it should be coming in as a copy.
You would think.
You could do something with it within that function.
Yes,
If you
it's
change
yours.
that function and it's coming as a copy, then outside the caller will
Ah,
this will be the same.
That's the key. The compiler will not copy only in situations where it knows there's no outside world to see.
So the compiler will check to see if there's any operation on that function, on that object within the function.
Right. So what the compiler is going to check is, it's going to say, is this an R value?
Okay.
Is this an anonymous, unnamed object that's about to disappear? If it is, then we don't need to copy it.
I did not know that.
It's a brilliant optimization.
Brilliant.
Send me an email and I'll send you a great blog post that explains it. So, line. Use critical line for the strong guarantee. Let's talk about the widget example again. Here's an implementation that I think solves what we tried to do. Here's our copy assignment. Here's our widget. What do I do? Well, I just create temporaries of these and I swap them. The reason Cargill said you couldn't do it is because Cargill didn't have swap. So I cheated by saying, oh, well, let's just assume we have swap. But that fits into my guidelines because my guidelines say we always have swap. Right? Look, critical line. Strong guarantee. Okay, I want to talk about one more topic here. Where to try and catch. Okay, so if you go on the session site, and why are you going to do that? You fill out the feedback, right? And then you're going to click on the wiki link, and the wiki link is going to take you to the bibliography, and you're going to read every book and article that's listed there. That won't take you longer than, well, you'll be back in time for next code camp. And you're going to get everything I've talked to you up till now. Well, except for that little optimization thing and a few things about system C++ 11. But you won't get this. Where to put the try-catch? This isn't huge, but other people don't talk about it, and I think it's important to talk about it. I think there's 3 places where we put the try-catch. And for handiness, I name them switch, strategy, and some success. By far, this is the important one, but these are also important. So, switch. Anywhere we need to switch our method of error reporting. So we're handling errors, we're reporting our errors by throwing an exception, but there are times when we need to switch. And if we need to switch, obviously we need to try catch, because we're going to switch. When would we need to do that? Well, anywhere where we have to support the no-throw guarantee. And where do we have to support the no-throw guarantee? In destructors, in swaperator, in cleanup code, right? We're going to have to catch, and we're going to have to figure some other way of letting the user know there's a failure or something. But also, let's suppose we're writing a C API. This is not uncommon at all, where we write a C API and we implement it with C++. The caller sees a C API, so it can be called from C or Objective-C or C++, any of these things, but the implementation is C++. If you do that, every single C API has to catch exceptions, because the C API cannot leak exceptions. No emission of exceptions. OS callbacks? Well, if you have an object-oriented OS, maybe it will take exceptions or something like that, but the vast majority of our OSs cannot do that. They're C API on the OS, and so we cannot leak callbacks. UI reporting, the user cannot, you can't throw an exception in the user's face, right? Somehow we have to translate that exception into an alert or some other way. And sometimes you may have a situation where you're saying, oh, I've promised that all the exceptions I am throwing will derive from this base class, and I may have other exceptions, so we have to catch in order to switch. But switch, that's the important thing. There's a couple other things, I'll just talk about it briefly. Strategy. Strategy means I have 2 ways of accomplishing something. If one fails, I have a fault. So let's say the user logs onto my system, and what do? I go out to the server and I download their preferences. They log in, I go to the server, I download the preferences. What if the server's down? Well, maybe I tell you, can't run the app. Finish. But maybe I say, oh wait, I cached your preferences last time. High probability those still work, I'll use those. Right? So I have a fallback. So how would I do that? Well, what I would do is, in the code where I'm calling, not the code that says the user's trying to log in, but below that, where I say, oh, I need to call the server, I'll put that in a try. Because if calling the server fails, then in the cache I can say, okay, I'll use the locally cached version. So that's an alternative strategy. The other one is some success. So imagine I have some app where what the app does is it goes and it polls all the servers to see who's up. Well, generally our model is that if you're trying to do something and you throw an exception, you tell the user couldn't do that thing. Right? If you're trying to print and the printer's down, you can't print. But here's a situation where some success is acceptable, or another way of looking at it is some failure is acceptable. We're trying to find all the servers that are up. If some of them are down, we don't give up. What we do is we put the try in a loop. Every single server that fails, we just won't report him as succeeding. No. So that's where we want to put the try catch. Know where to catch. Switch, strategy, success. This is the important one. Now I want to talk about something else. The most important design guideline. This is an article written by Scott Myers. Remember, one of my idols. He's on the bibliography. He actually put this with a question mark because he wasn't sure, but I think he's probably accurate. C++, Scott's known for his C++ advice, but this article had nothing to do with C++. He's saying this is a universal design principle, and I would argue that when you hear it, you're not going to disagree. Here's what he said. Make interfaces easy to use correctly and hard to use incorrectly. Who disagrees? We got to keep those users on their toes, right? And this is, you know, if he's driving along and he's not paying attention, then razor blades should shoot out of the steering wheel, right? Okay, so this, I argue this is mom and pop. And this has nothing to do with C++. In fact, it has nothing to do with coding. It's just design, right? Make it so that when you grab the thing, the way it's comfortable and convenient to grab is the way it's supposed to be used. All right, so let's apply that now, this general design guideline. Let's apply it back to C++. Suppose we have code that can be implemented to return error code or a function that throws instead. If the definition of use correctly is don't ignore the error, which one's easier to use correctly? Which one's harder to use correctly? So here's the guideline. Prefer exceptions to error. I know that's controversial, but I think it follows from the most uncontroversial concept in the world. I want to say a few things about this. First of all, throwing exceptions should mostly be about resource availability. So we've talked about that, right? Notice that generally for state, we don't throw. For not leaking of state, we still want to treat it as if, treat it the same way. Do you follow what I'm saying? In other words, you're probably not going to throw trying to set the foreground color to read. But we still treat that as a responsibility, and that's part of exception-safe coding, even though it has nothing to do with exception. When possible, provide defined behavior and use strong preconditions instead of failure cases. In other words, try to write your code in such a way that you've made the precondition, made it an assertable failure, right? You should be in the right state before you call. The burden is on the caller to be in the right precondition. Don't use exception specifications for general flow. We've already talked about a few things about this. Performance will suck. Lots of things wrong with it. In general, though, if you find out that you're getting exceptions in the regular code path on a regular basis, you probably have a design. Now, what I want to say is, I've made this real simple. It's all white and black. I understand. There are times when things are gray, right? So let's say I'm trying to read from a file, and I hit the end of the file. I can't read. Well, is that an exception? It's an error. It's an exception, right? Well, that means that every time I read a file, I'm going to be throwing an exception, right? So that may be a gray area. You may want to think about what you're doing there. But anyway, as long as we can keep it at a high level, it's really black. So here they are. Throw by value, catch by reference. Destructors that throw are evil. Do not use exception specifications. Use RAII. Remember, every responsibility is an object, one pro. All cleanup code, call from a destructor. Create the swap operator, remember, no throw. Draw critical lines for the strong guarantee. Know where to catch, switch strategy, some success. Refer exceptions to error codes. How are we doing on time? I'm already out of time, right? I'm happy to stay and go through. I've got some really important stuff. I'm sorry I went over. I tried to go fast. Are there any questions about this? Okay, I'm going to talk about some implementation stuff. This won't take too long. The first thing I want to talk about is a class that I wrote called onScopeExit. I'll just give you an example of it here. And it's basically what you were talking about earlier. What we do is we bind a function call with its data object that simply calls that function when it goes out of scope. The idea here is that we don't really want to write a class. If you're calling some cleanup function only once in your entire application, you may not want to write a class to it. So this class is a template that handles that for you. It just calls whatever function you give. And you need to know a little bit about bind, which is now in the new standard, and so you can know how to bind stuff. So I want to talk about Lippincott functions. This is a technique for refactoring exception handling. So I worked on a project where I had a C API over a C++ implementation, and it had 2,000 entry points. And this was very, very old legacy code. Lots and lots of engineers had worked on it, and we had many, many kinds of exceptions. We had exceptions from a framework, we had exceptions from utility classes, of course standard exceptions, all these different exceptions. All of them have a different way of getting from the exception to the error code. And so we needed to do this for every one of our 2,000 error entry points, right? We need to call the C++ code, and if that were to throw, and I've written this poorly to get it all fit, but essentially we have all these different exceptions and then we get the result and then we return the result, right? So what happens after we do this and have this in 2,000 different entry points, and then somebody notices, oh wow, there's some code in here that we didn't even realize we had, throws a different kind of exception. Or maybe we want to start using a new library that throws a different kind of exception. Or maybe we identify some new error codes that we want to change, right? So we want to maintain this. This same code is copied in 2,000 places. That's not good software engineering. How about if we could do this? How about if we had a single function that said, get the error from the exception? And we just call that. This is a Lippincott function.
A what?
A Lippincott function, named after Lisa Lippincott. She didn't even invent it, she just told me about it. No, she did a lot of popularization to tell people how to use it. So here's how it works. What happens is, we call our Lippincott function, and it first thing it does is, it throws. Remember, we said, wait a minute, rethrowing when you're not in a catch block, that's one-way ticket to terminating your end. But we are in a catch block. We got calls from a catch block, right? We're in a catch block. So it's safe to rethrow. The key here is the compiler, the runtime realizes we're in a catch block. You don't have to, you know, we normally think, oh, you have to rethrow in here. Well, you do. You have to rethrow in there, but it can be in a function that's in there. So that's what the Lippincott function is. So all that ugly stuff that I saw before, it's just repeated here. That's all. Okay.
That's where you have all the definitions of all the exceptions and how they're handled.
Yeah.
So it's 9 miles long.
Yeah, but it's in one place.
Right.
And it's called 2000. By the way, in classic C++, there's no safe way to know that you're not in an exception handle. In other words, you can't write this so that some idiot calls it in the wrong time, you've aborted. Right? But in C++ 11, there's ways to do this. So boost exception. Boost exception has one interesting characteristic. So one of the things that we can do in exception, remember we're catching by reference, right? Usually we want to catch by const reference because we're not going to modify the exception. But it's possible to catch by reference and actually modify the exception. That's what boost exception is for. Boost exception, I would say, is not a general thing, but in a situation where you want lots of good debugging or troubleshooting information, the way boost exception works is it defines a way that you can add information to an exception as it's being propagated back in. So let's suppose at the bottom layer you have somebody who says, oh, I don't have permissions to write this file. So he creates an exception, a permission exception, and he throws it. At the higher level you can catch that and you say, well, the file name was X. Think about it. Most of our functions that read and write files don't know the name of the file because the file got opened at a higher level and then passed in, right? So if you try to create an exception and say this is the file that failed, I don't know what the file that failed is. I just know a file failed. So you catch it at the higher level and you say this is the file. And at the higher level than that, you say this is why I was trying to read the file because I was trying to create the print spool, right? So instead what happens is at the very top you can put up an alert and you say, you know, had permissions error trying to open this file while printing. Otherwise you would have just said something that said, you know, error because of permissions while trying to print. It's like, well, my printer doesn't have permissions. What is that? So it's not, I didn't spend, there's some cool stuff in it. It's a question about whether or not it is an exception to this. You might say it's actually part of switch, but whatever. This is really important. transitioning from pre-exception, exception, unsafe legacy code. How many of you worked with that before? Oh, come on. No, everybody got their hand up, right? Okay. But you'd like to be in the exception safe world, wouldn't you? Come on. I got you excited about it, right? You'd like it. How do we get there? The problem is our code doesn't handle this code path disruption gracefully. Sean Parent's iron law of legacy refactoring. This is not going to solve your problem, but it's going to give you the guideline for how to get there. Existing contracts cannot be broken. So if you want to write some new functionality and you say, I want to use exception safety to make it easier to read, easier to write, easier to maintain, it's faster, all these things, but I can't introduce exceptions into this clunky old code base. Some function that exists in that code base is going to make the call to your new code, and you're going to need to wrap that in a try-catch. Because that function's contract can't be modified. If it currently isn't expected to throw, then you have to honor that. So what happens is, painful at first, you create two versions of everything. You create the one that throws, and then you call from the one that doesn't throw, and you put try-catch. But as you add more and more code, you begin to retire these ugly wrapper functions. And eventually, you wake up one day and you're in the world of exception safety. So I want to talk a little bit about before and after example. So I wanted to show what's the day and night difference. So I was a Mac programmer, so I went to Apple's website, and I said, I looked for this, I kid you not, this is the first example I saw. It's about creating, you probably can't read, you don't need to. It's creating an ACL, and it's calling all these functions, and then each one it checks to see if the result is 0, because if it is, we can proceed, but if it isn't, we're going to have to free it, and then when we're finished, we return the ACL. Right? I kid you not, this is the first one I saw. So I said, okay, let's make some assumptions. The first assumption is, I'm going to create a wrapper on the ACL, and here it is. It's really pretty short, but it's a RAII, right? So I initialize the object. I initialize the object in my constructor, and then in my destructor I free it, and then I have a release member, right? Okay, and so I rewrote this. This is the same code as before, except I'm using this, and I'm making the assumption that each of these functions, instead of returning a value, throws on error. Right? Do you see the difference? You see the difference between that ladder logic and this? Okay, so I took it one step further. I said, okay, this is following Sean Parent's iron law of code refactoring, which said that the previous code always returned a value, did not throw. But let's suppose I'm in an enlightened world where I am in a code base that did throw. So what does that look like? That looks like this. I create the apple, I release it and return it. If I throw, I am counting on the people who are calling me to catch. Right? This is intermediate code, which means I neither detect errors and throw or handle errors. It's intermediate code. It's not the lowest level. The lowest level are these ACL functions that are going to do something that might throw. And it's not the highest level, it's not handling it. So there's no throw or catching. So I have this wrapper class. Look at this. 50% fewer lines, 100% fewer braces, 100% fewer control structures. I kid you not, it was the first example I saw. I didn't cherry pick it. This is what makes me excited. So what does exception safe code look like? There is no try, according to you. He's exaggerating, yeah, you gotta try. It's the coder's fantasy. What would you like to write? Would you like to write code that doesn't fail? Wouldn't that be cool if you just could assume it doesn't fail? Well, at the low level, you can't do that. And at the high level, you have to handle it. But all the code in between, it's like it doesn't fail. You just write the success path. Just write the success path. That's the power of the coding. I have a friend who tells me the way he does it is, he writes his code without worrying about it failing at all. And then when he's finished, he goes back and he says, what could fail and what will go wrong if it does? But because he's using the exception safe method, he says, almost always, I never touch anything. It just cleans up, right? I'm just writing the success path, and it just cleans up. If you do it this way, it'll be easier to write. You saw half as many lines. I didn't have any control structures. I don't have to worry about the failure case. Much easier to write. Is it easier to read? Well, you tell me. You just read line, 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 instead of, okay, now if, all right, okay, you're checking for this stage. No, you just zoom, right? Is it faster? Yeah. Just think about it. I'm checking to see if it failed at this level, but then when I get up here, I have to check to see if it failed at that level. Check to see if, remember, when we're in a try, the try is free. Right? 100% robust.